the air conditioner in your room, for example. Yeah, this is also engineered using the principles of thermodynamics. So we see the applications of thermodynamics are around us. You can find it everywhere nowadays. A short story about the thermodynamics as a scientific discipline. So I think we can start with the German scientist Otto. Yeah, here I took a picture of him on the internet. Actually, Otto, he was the first one who built and designed the first vacuum pump. Yeah. So we even have the Otto cycle. He was the first one who built and designed the first vacuum pump. Something related to the thermodynamics. And then after that, we have Robert Boyle. He is actually an Anglo-Irish physicist and chemist. Okay, he and Robert Hooke, the second one, he was an English scientist. They together built an air pump. So I think the Boyle and Marriott principle, I think you heard about it, định luật Boyle Marriott. You should heard about it, right? So actually, this is him, Robert Boyle. And then later on of the 16th century, we have Denis Papin. Denis Papin en français. Okay, he is a French physicist and mathematician. He built a steam digester. This is another application of thermodynamics. Denis Papin, because his name is in French. Then here comes the very famous Nicolas Léonard Sadi Carnot. He is also French. Okay, Carnot. Actually, he was named as the father of thermodynamics. He's very famous. I think maybe some of you already heard about him even before going to this slide. Okay, we have the Carnot cycle, right? We will talk about deeply about the Carnot cycle in the last chapter, the last session of this subject. So he was named the father of thermodynamics, and he published a publication named Reflections on the Motive Power of Fire. This was actually a discourse on heat, power, energy, and engine efficiency. Okay, so he was the first one who found the maximum efficiency that one real engine can attain. Actually, we can never attain the Carnot efficiency for one real engine. So he set the limit for the efficiency of an engine. Okay. And later on, we have William Thomson. I'm sorry, not yet. Here I missed something. Anyway, we have Gibbs. He was actually American mathematical physicist. And he was the one who showed how the thermodynamic processes could be graphically analyzed. Okay, how the thermodynamic processes could be graphically analyzed. We are going also to analyze some thermodynamic processes using graphics in our subject. And during the early of 20th century, we have several famous names. We have Gilbert Lewis, we have Mertley Randall, okay, and so on. So they applied the mathematical method subjects to the analysis of chemical processes. And here, starting from here, we have the whole thermodynamics as a scientist discipline. Okay, and here we have set up a big enough field of thermodynamics. And then we could also divide the thermodynamics into smaller branches. What are they? So we have normally 4 branches of thermodynamics. We have classical dynamics, thermodynamics. We have statistical thermodynamics. We have chemical thermodynamics, and we have equilibrium thermodynamics. So for the classical thermodynamics, we here in this branch, we try to describe the states of thermodynamic systems at near equilibrium that uses macroscopic measurable properties. So it is used to model the exchanges of energy, of the work, and also the heat based on the thermodynamics law. Okay, we are going also to study some thermodynamics law today. So this is for the classical mechanics, what we are going to learn. For the statistical thermodynamics, so in this field, we try to relate the microscopic properties of the individual atoms and molecules to the macroscopic, the bulk properties of material. So therefore, we can explain the classical thermodynamics as a natural result of statistics, of classical mechanics, and the quantum theory at the microscopic level. We will go deeper into some definitions of the terminology, what is the microscopic properties, what is the macroscopic properties, and so on in the next slide, okay? But this is for the statistical thermodynamics. For the chemical thermodynamics, actually, this is the study of the interaction of the interrelation of energy with chemical reactions or with the physical change of state within the confines of the law of thermodynamics. Okay, so that's why you will see in the second semester when you study the general chemistry number 2, there's one part you will see that this is very similar to what you have learned in the thermodynamics, yeah, during the second semester when you study the general chemistry 2. Yeah, because the thermodynamics are applied into the chemistry field also. And then finally, we have the equilibrium thermodynamics. This is actually the study of transfers of matter and energy in systems or bodies. So that can be driven from one state of thermodynamic equilibrium to another. We are going to see in the next slide what can be called thermodynamic equilibrium. Okay. But here the terms thermodynamic equilibrium, it indicates a state of balance. Okay, we will have different states of balance. I'm going to show you in the next slides. Now we go to the first concept, which is very important when we study the thermodynamics. For the thermodynamics, we should understand firstly what is an open system, what is a closed system, and what is an isolated system. Okay, so open system in Vietnamese là hệ mở này, closed system hệ đóng này, isolated system hệ cô lập. I'm not strong in Vietnamese, I can tell you, because I do not follow the Vietnamese program. So I studied in Europe for more than 7 years, so I'm not good at Vietnam. Try equivalence for you. Okay, so if you have time, you can go to the internet and you can find for Vietnamese book. Yeah, you can find a correct translation, for example. Now, in an open system, what do we have? In an open system, we have both the interactions between the energy and the mass. Okay, both the energy interactions and mass interactions will take place. Here you can see here, please see the mouse. Here this is an example of an open system. Okay, we have a pipette which is open. So we can have the interaction, the transfer of energy between these, between what we have inside here and the outside. So we have the energy interactions and also the mass interaction. So this mass might change. This might go outside. So we consider this is an open system. For a closed system, in a closed system, only the energy interactions and no mass interactions takes place. Okay, only the energy interactions will take place. The mass remains unchanged. This is the example of a closed system. We have the same thing. We have the same pipette. But now we close it. Okay, we close it. Totally, we close it. What will happen? The mass remains unchanged. There's no transfer of mass anymore. No mass interactions anymore between what we have inside and what is outside. But this system can still do work. I mean, they can interact the energy. For example, if you heat it, the mass will remain unchanged. But maybe because this is expanding due to the heat, then you can create some work, right? So there's the energy interaction, but there's no mass interactions. We call it a closed system. Please remember it. And for an isolated system, This one, no energy interactions and also no mass interactions takes place. Okay, this is the example. Sorry. Who lets the mic on? Please turn it on.
Lao sao?
Chị không nói chị không? Số em cứ tăng, em sợ là ngày nào cũng có mấy em mất không chị không?
Dương Đoàn Trần Tuấn. Okay. Please let your mic off. If you have any questions, you can turn it on. You can ask me directly. But if no, please turn off your mic. Yeah. Thank you. So let's go back to the isolated system. So this is the example of the pipette, this one. But now we have an insulation, a very good insulation here. Yeah, a very good insulation. So here, there's no energy interaction. This cannot be heated up. So we have the same temperature, for example, then there's no energy interaction, either in the way of heat transfer, either in the way of doing work. Yeah, there's nothing. So now no energy interaction, and of course also no mass interaction. We enter to the case of an isolated system. Jose, okay, is it clear for you? System, open system, closed system, and isolated system. These are the very basic concept of thermodynamics. We should be able to understand it. Okay, then we continue. We talk about the microscopic system. And of course, related with a microscopic system, we have a lot of macroscopic system. And related to the macroscopic system, we have a lot of macroscopic properties. So we say that the macroscopic system is concerned with the effects of a certain number of matter. A certain number of matter, not one molecule, not two molecules, but it should be a certain number of matter. And these effects can be perceived by human senses. So we can see it, we can sense it, okay? We can perceive it. So we call it a macroscopic system. Related to macroscopic system, we have macroscopic properties. These are the properties associated with a macroscopic system. For example, we have pressure, okay? We can sense it, right? We can perceive it. So pressure is a macroscopic property. We have volume. We have temperature. We may have even density, composition. We have viscosity. We have surface tension. We have index. We have the color, and so on. These are called the macroscopic properties. Okay. Inversely, of course, we have microscopic properties and microscopic system. So the microscopic system is concerned with the effects of the action of molecules. Okay, the action of molecules. And these effects cannot be perceived by human senses. So you see, the macroscopic, it can be perceived by human senses, while the microscopic system, it cannot be perceived by human senses. So for example, sorry, who's speaking? Okay. Bạn nào nhỉ? Tắt mic của tôi cái. Okay, for example, for microscopic properties, we have maybe molar mass. Okay. Maybe we have the velocity of atoms, of molecules, and so on, things we cannot perceive by human senses. We have momentum, we have kinetics energy, potential energy, etc. These are called the microscopic properties. Yes, Vietnam mind.
Can you re-explain what is a microscopic system? I don't understand clearly.
Okay, I mean, when we say something that is macro, that is something is related to something that is big, okay? And we say micro, so you see micro, it should be something small. Khi mà ta nói tới một cái gì đấy nó là macroscopic, có nghĩa là nó là một cái gì đấy nó lớn, đúng không ạ? Khi ta nói tới cái từ micro này, microscopic, thì nó là một cái gì nó nhỏ, đúng không? Theo nghĩa mà chúng ta hiểu một cách rất là thông thường đó. So here, macroscopic system, we talk about system that's big enough. Yeah. Okay, that is big enough. Then, I'm sorry, here, we talk about the effects that we can, for example, we can see it, we can sense it, we can perceive it. We, our human, yeah, using human senses, we can see it, we can perceive it. So we place it as a macroscopic system. Related to the macroscopic system, we have the macroscopic properties. For example, we have the pressure, so we can sense it, right? We can perceive it. We have the volume, so we can define by our human senses. We can understand, we can know what is the volume of this one, what's the volume of the other one. We have temperature, we have density, and so on. For the microscopic system, we are entering the systems that are very small. So we cannot see it, we cannot perceive it using only our human senses. For example, the velocity of atoms. Can we see it? Can we sense it? I don't think so, right? Or the momentum, or even the kinetic energy. Yeah, we cannot perceive it by human senses only. Is it clearer for you?
Yes, thank you.
Oh, thank you. So I think we can move on. So macroscopic, very nice. And now we enter to some other basic concepts of thermodynamics, which is intensive properties and expansive properties. Or you can see in other words, we have intrinsic properties and extrinsic properties. These are the same. Okay, intrinsic properties or intensive properties. So these are properties that are independent of the mass of the system. Yeah, independent of the mass of the system. Inversely, we have the extensive properties. So these properties depend, I'm sorry, yeah, I have a mistake here. Yeah, the extrinsic properties, these are dependent of the mass of the system. Some example here, the intensive or the intrinsic properties. What do we have? We have, for example, the boiling point. Okay, so this is independent of the mass of the system for sure. For example, water. The boiling point of water will always be 100 degrees Celsius. It doesn't like if you have 2 kilograms of water, the water will boil at 50 degrees Celsius, right? So we have color and so on. Maybe the hardness, the temperature, the luster. And for the extensive properties, here these properties are dependent on the mass of the system. The mass itself is an intensive property. We have the volume, for example, we have the length, dependent of the mass. So we have the weight, of course. Okay. The size, for sure. Now we go to another basic concept. I think we have 3 hours, right? Working together. We go to this. Okay, I finish it, and then we take a break of 10 minutes, right? Normally it's a break of 10 minutes. Here, when we talk about the thermodynamic system, we should talk about the state of the system. So a state is defined by specifying the values of a set of measurable properties sufficient to determine all other properties. For example, here, the state of fluid systems, the state of the fluid systems. This will require typical properties such as the volume, the temperature, the pressure. Okay, so when we know the volume, when we know the temperature, when we know the pressure of a fluid system, we can define that this is one state of the system. When we change, for example, just one property, the volume, for example, when we change the volume, we have another state. When we change the temperature, we have another state, and so on. Okay, this is the state. And the process. We define the process in terms of thermodynamics as any change of state of the system. When we make a change of the state, any changes, we say that we have a process. We have a thermodynamic process. Along with the process, of course, we have the process path. Okay, if we go from one point to another point, we can go by different paths. The thermodynamic process is also the same. If you go from one initial state to a final state, you can go by different processes, by infinite processes. Okay, but each path is called one process. Okay, is it clear until here? These are very basic concepts that you should remember. I think we can stop it here a little bit for 10 minutes and then we go back. Okay.